Welcome to the CLSP seminar. Today's seminar is somewhat special. It is going to be a special seminar in a series that will continue over many years, we hope. The special thing is that we're getting some of our own people back. So Xiaoqiang is our speaker today. Xiao came to Hopkins even before CLSP, or maybe about the same time as CLSP, but definitely before Fred Jelinek. And he was in fact our first graduate. When we started this seminar series, also about 8 years ago, we were of course looking for prominent people in the field to come and give lectures. And almost 10 years have gone by, and we're starting to realize that some of the more fun people in the field are indeed our graduates. So it's a pleasure to welcome Xiao back. Xiao came to Hopkins from China. He got a bachelor's degree from the Chinese University of Science and Technology, but of course his PhD is from here. So to some of you, or some of the faculty, for example, he doesn't need any introduction. Perhaps, no, there's no one here who overlapped with you. Oh, there. No, David, you don't count, but okay, Hans and Silvio. So we're seeing the passing of the guard, the changing of the guard. Here are the new people, and this is what we're aspiring to. Xiao, without further ado.
Okay, thank you, Sanjeev. It's a pleasure to come back. Okay, today I'm going to talk about the work we did in the last few months about using cross-domain data to improve our statistical parser. This is a joint work with Min Tang. He did a summer internship in this summer at IBM. Okay, so before I talk about the topic, I want to take this opportunity to tell you what, as a group, as an NLP group at IBM, what we have been doing, certain projects we have been doing. The statistical parsing started almost a decade ago, and we have used this technology in many applications, natural language applications. I list a few here. The first is we have been using a distributed-based statistical parser to build a language understanding component in spoken dialogue systems. And the same technology has been used in information extraction, translingual question answering, entity extraction, so on and so forth. And Kishore and his team are working on statistical machine translation these days, focused on two language pairs from Chinese to English and Arabic to English. There are also a few people are doing cross-lingual search, TDT, text categorization, and audio indexing. This is a Malloc project. I won't take questions for this slide because first I only know some of the items well. And second, I think the best way, especially for students, if you want to find out the details, the best way is come and join us. Our group is still actively hiring, so if you're looking for some job or close to graduation, so please do send us resume. Okay, so let's get down to the business. I'm going to start with the motivation of this work, and then I'm going to talk these items one by one. Okay, so we all know that the impact of training data for statistical parsing and for statistical modeling in general, for example, speech recognition. This curve shows that the F measure on Wall Street Journal Pantry Bank, x-axis is the amount of training data. This is the one basic parser. As we can see that if we increase the amount of training data, the more training data we have, the better performance is. But then the problem is that to acquire more data, especially with full tree labeled, is quite expensive. So there's an issue that there's a need to reduce the labeling work. For example, use unsupervised method, or maybe semi-supervised method. Here I list a few work that on this track. For example, in '97, Xiaoqiang used his parser parsed about 10 million or maybe 30 million words and put it back in training, and he reported small gain. And Brahman and Mitchell proposed a method, so-called a co-training method. The basic idea is that he assumes that for a problem you have a two independent view of training data, and you can build two separate models and use one model to annotate data for the other model. The past workshop, a group of people explored the same idea for statistical parsing. And in 1998, Andrew, McLean, and Nagan used mixed labeled and unlabeled data for the document classification. They used the EM algorithm to infer labels for unlabeled data. And you'll see this is basically we are going to use the EM algorithm in the same spread. In the past few years, we have been doing some work also on this track. In IEEE, a workshop for automatic speech recognition and understanding, I used a transformation-based method to adapt a statistical parser. You can find the details in this paper if you're interested. And in this past year, we did some work in active learning. You can find a paper in ACL this year. So let me talk a little bit more details about active learning. The basic idea of active learning is that compared with, say, passive learning, is that passive learning, you ask a human being to label a certain amount of data and build a statistical model. So it's a monolithic process. Whereas for active learning, you say you start with a certain amount of initial training data, and you build a model. And the idea is that you want to use this model to pick from a large unlabeled data a subset to label. So the idea is to want to reduce the amount of labeling work. So this is a learning curve we got in the domain of a data communicator.
Are you going to say how you pick that subset?
No, that was in the ACL talk. I don't have time to cover that. But I just want to give a result summary here. The curve in red is the learning curve for active learning, and blue is you are randomly selecting the same amount of training data. The dashed line is that if you labeled all the training data you have, that's the performance bound. As you can see that the active learning can approach the performance bound much faster than random selection. There's a value if you want to develop a system at the early stage. If you use active learning, you can get much better. Basically, you can get the same level of performance much faster than, say, you just annotate all the training corpus. Okay, so but the bottom line for active learning is that you select a subset of training corpus, but you have to do some annotation. So the work I'm going to talk about today is that can we not do annotation at all, but instead we're looking at, let's say, cross-domain. I'm going to use cross-domain, cross-corpus interchangeably. By cross-domain, I not necessarily mean that a different giraffe of tags, but by say labeling for a corpus is different from the domain we're interested in. This will become clear after I give some examples. And we want to take advantage of the labeling work done for other purpose. Now the next question is that, for example, if I take the Wall Street Journal Pantry Bank, can we find useful cross-domain data? So in this table, I list a few examples that we think that are potentially useful for improving parsing accuracy. On the English side, we have in-domain data, Wall Street Journal, Pantry Bank. And at IBM, we have another tree bank annotated in for a corpus of AP News article, but the annotation is very different. I'm going to show some examples. Another potential source is that we have a corpus with name entity annotation. So maybe we can use some information from this corpus, for example. We have been also working on the Chinese parser, and LDC released 2 batches of tree banks. So this is our in-domain data. And recently we became aware that Beijing University in China, they have annotated a lot of data with part-of-speech tagging. So this is a potential useful, although the part-of-speech tagging style is very different from Pantry Bank. And we also have about 500,000 words Chinese corpus with name entity annotated. So these are a few potential corpus that will be useful for us. And I claim here that cross-domain data provides some but not all information for the purpose of parsing.
So, in case of the Chinese, what is the source of the Chinese Pantry Bank and the Chinese, the PKU?
PKU is People's Daily. It's 1 year of People's Daily. Pantry Bank, I don't know what's the source, but it's also general news articles. And the name entity is FIPS. Okay, so let's take a look at the, this is an example of AP tree bank. That's the tree we found in this tree bank. And the same sentence, if we annotate it in Pantry Bank, Wall Street Pantry Bank style, that's the parse tree. So I just want to highlight a few common constituents in these two corpora. For example, the first NP constructs and this VP. So let me go back to the last slide. See, although AP tree bank has different label, but you see that this constituent is common in both corpora. And so is this VP phrase, and so these are sentence segment. So it looks like at least we can use. So starting from AP tree bank, if we can do something to migrate, at least we can get a partial information from the AP tree bank. Of course, there are. It's not always that you can do direct mapping. For example, in that's the style of Wall Street Pantry Bank style. You have unary constructs S goes to VP, which is missing in the original AP tree bank. And sometimes there's more serious problem of cross-bracketing. So this is one sample sentence I found in the AP tree bank. That's the AP tree bank style of annotation. For some reason, the design of that tree bank decides this is a constituent. And I found almost the same sentence segment from UPenn tree bank, although this is a current complete and this is a faster completion. But see, the UPenn tree bank design says this is one constituent. So clearly there's a cross brackets. So we have to be careful if you want to use brackets directly. Okay, now let me, in the next few slides, talk about the PKU part of speech tag corpus. The PKU corpus has 67 part of speech tags, and the UPenn tree bank released by LDC has 33 part of speech tags. They are, after we look at the two corpora, we found there are various types of mapping if you want to map a power speech tag. For example, the one-to-one mapping, the noun in a PKU can be directly mapped to this tag in UPenn. And PKU has a personal name tag and organization name tag. Well, in UPenn tree bank, you only have like one proper noun tag. So these two power speech tag goes to the same tag in UPenn tree bank. And sometimes you have one-to-many mapping. For example, this word it's an auxiliary word in PKU tree bank, and the design of the Penn tree bank decided that this auxiliary word has two syntactic rows, and it is assigned two tags based on the context the word is used. Sometimes we have more difficult cases. You have this is a pronoun tag, and this is a pronoun morpheme tag, and this tag sometimes can be mapped in a UPenn tree style as a determinant. Sometimes it's a pronoun, and so is this tag. So we have many-to-many mapping. Okay, this is an example sentence segment. Words in blue are the first category of a mapping, either is one-to-one or m-to-1. And the words in red is that it's one-to-many mapping. So what I did is that I look at the context. If I can resolve the ambiguity based on limited context, then I will say that I will use the tag. Otherwise, I'll remove I'll say that I don't know the tag, the corresponding tag in the UPenn style, and but insist that this is a word boundary, because in Chinese we have this problem of word segmentation problem, and sometimes there's a style difference. One word, for example, in PKU style may not be one word in the UPenn style. So if that is the case, where I dropped even the boundary, word boundary. And this is summary result. By doing this, this is a lightweight processor. We can map about 93 words from PKU corpus into a Penn tree bank style with UPenn style or power speech tags. And 6% of the words I can keep a word boundary. And there's only about 1% of words that I'm not sure about the tag and the even word boundary.
So Xiao, this mapping between the tags, this is obtained only by knowing the UPenn tree bank tag set and the tag data from PKU. You don't need any tag Penn tree bank data to discover this.
In fact, I looked at that. I got help from one of my colleagues. I looked at both, because you have to really make sure that this mapping is accurate.
Well, so that's my question. If your goal is to take the Chinese PKU tree bank and construct a parser that will parse like the UPenn tree bank, then you shouldn't assume any existence of UPenn parsed data. Or are you allowed to yourself some?
This is not automatically. This is
this is manual, but
right.
There's one thing where you just use the tag set and sort of you have like Mitch Marcus or somebody has a grammar and a text or Martha Palmer, you use that information to construct this mapping.
Yeah, but in any case you have to know the meaning of what is the category for a part of speech tag in the UPenn. You have to what is the syntactic category, right? You have to have that knowledge. Okay. Yeah. Okay. So the message by looking at these various corpora is that looks like we can convert the labeling information in cross-domain and represent that information as constraints as a partial tree into the domain we're interested in. And when we do that, we have to make sure that in what granularity we do the mapping.
I understand it in the part of speech case, but I don't understand it in the structure of the parsing, because how do you know that some section is parsed the same way?
Yeah, that is this question. It's not automatic. We have to look at the two corpora to.
I see. So you open. No. But I mean, in a particular sentence.
Yes.
How do you know which part of it you can use?
Yeah, this is a question. We don't really know the answer, especially if without looking at the data.
So are you proposing to look at the data?
Yes.
I see. So you're just going to save the labor of parsing it, but you will still decide whether it's acceptable or not.
Yes.
I see.
Yes.
Oh, on a per sentence basis?
That's what it seems to be saying.
Are you saying you're going to look at every sentence and decide what's right?
No, not saying. We're looking at some example sentences, and
Oh.
no, we're not going through each sentence in the corpora.
Okay. Well, I don't understand how you can decide in general that a certain parse structure is the same, would have been the same in UPenn 3-bank.
Yeah, we don't know the answer for sure, but there's certain things we can do. For example, we did a few experiments, for example, keeping all the brackets, but there's an issue, as I showed in one example,
Yes.
You have cross brackets.
Right.
And we also did, by one rule, for example, keeping the highest constituents. Yeah.
Okay.
But the bottom line is that you have to look at data, see how useful a particular corpus is to you. Anyhow, so we looks like we can get some information from cross-domain data. But what about the structures that are missing? And that is where the EM algorithm comes in. So we treat this as an incomplete data problem. Let's say we get partial parse trees from labels in a cross-domain, and get a partial tree. The completed data is going to be the missing part together with the partial tree. All right. And our goal is that we want to learn a model that maximizes the probability of the partial tree partial trees that are available to us. Okay. So let me give you an example by what I mean. What is the partial? For example, take the AP tree bank, and by looking at a few examples, let's say we are sure that the highest a constituent we want to keep. So in this, if we made that decision, then say all the constituents in solid rectangle are the constituent we want to make. We want to keep, and everything in dashed line are something missing. Okay. So in this example, constraints is that we know this is a constituent, but we don't know what is on top and what is underneath of that label.
And how do you know it's a constituent? Because you have.
Oh, this is you have a parse tree in the AP tree bank, right?
Okay.
For example, for this example is you made there's a rule saying that I want to keep the topmost constituents.
So the topmost NP is going to be kept
Right.
in tree.
Right.
So you believe that those will be NPs no matter whether you did it AP style or UPenn style.
Right.
But underneath that NP, you don't know what's going
I don't know. Yeah.
And you don't know at these top level things how they're going to be connected.
No. Yeah. So that's what I meant by a partial tree.
So in terms of labeled brackets, you're pegging some brackets and you're removing the others.
Mm-hmm. Right. Okay, so this is a missing data problem. To maximize this quantity, EM algorithm states that all we have to do is maximizing at each iteration. We maximizing the auxiliary function, which is a conditional expectation of a completed data, S is a sentence, theta is our model parameters. Taking the conditional expectation, write it out, that's the formula we'll end up with. So if you look at this formula closely, let's say if all the information is given, well, so the Tm is empty, so this term, the term inside the summation is independent of Tm. Tp partial is the same as T, then these two terms cancel out and you get it back the normal likelihood formula. All right, to implement the EM algorithm, so we needed the facility to do constraint decoding because we get constraints from our cross-domain data. We treat partial tree labels as constraints. And we found the missing labels consistent with TP. So all the decoding results that are inconsistent with that partial constraints are going to be discarded. And in practice, we have to do pruning. We can't possibly do, so far we haven't figured out a way to complete, say, the counterpart of forward-backward training. So we do top-end training. And in the course of doing that, we found that, because we have to do this again and again, so we spend quite a bit of time to speed up the decoder. We get anywhere from 2 times to 16 times of speed up based on our decoder is a beam search decoder. So depending on how wide your beam is, the more hypotheses you search, the larger the speeding factor is. Okay, so so I've talked about the processing cross-domain data to the domain we're interested in, and I talked about EM algorithm to deal with the missing information. So here is the picture that the process we're using in this semi-supervised learning. We started with a certain amount of in-domain data, build a model, and take the cross-domain data, and we have to do some pre-processing to map the labels in cross-domain data to partial tree constraints to the domain we're interested in. And then we take the model.
So in the first arrow, that's when you get these the blocks you were showing in the earlier.
Yeah, for example. Right.
Can you break it down further? So can you say that, for example, if I had a sentence in which I knew 4 of the blocks, so can I then break it down into 4 examples where the top of that subtree is going to be an NP or a DP or whatever?
What do you mean by
I mean, within that it's a separate, you can decode each part separately, right? Because you want to know what's inside underneath the NP.
Yeah, but after you do that, you have to find the construction on top of NP.
Okay. Is the rest of it context free, so the other 2 probabilities in the event?
We're using statistical Parsers, so we don't have an explicit context free rules. Okay, so you take the partial tree as constraints and do a constraint decoding. And in essence, and then we take the decoding output, put it back in the training with the right counts. And then update the model, so this is a closed loop. Okay, any questions before?
Before you go on, I just want to be clear, how are you using the fully labeled tree bank? Are you using it to construct a trier, or are you just using it to seed the model?
We use the seed model after we use that seed model to build use the fully annotated corpus to build a model, and we're going to use both the fully parsed tree and the decoding output with partial constraints.
So they stay with you through the whole EM process.
Right, right. There's no reason to ignore that corpus.
But do the others get the equal weight?
No, they don't. That's the E step you take to do right counting.
No, but
No, the fully parsed tree always has a count 1 for sentence.
yeah.
For the decoding output, whatever the probability the model gives, you keep that as a count.
Well, then you're giving it full count because you distribute the count but the total that you distribute is 1.
Yeah, total is
also.
1, yes.
So whatever you get from the, not wrong, but from the auxiliary corpus counts as much as the other.
Yes. Yes. Yeah, the statistical parser we used in this work is max entropy parser. You can find the reference in Adwey's paper, 97 paper. We have two parsers. We have models for two languages. On the Chinese side, we have a U-Pantry Bank. They're released in two batches. First batch is 100,000 words. Second batch is about 120,000 words. The cross-domain data we used is the PKU 1 million words with a part speech tag, but without a parse tree. On the English side, the in-domain data is 1 million words at U-Pantry Bank. And we have this AP tree bank, also about 1 million words. These tables summarize the experiment setup. Okay, let's start with Chinese side. The experiment labeled with CE1. The baseline is trained with the first release of U-Pantry Bank. The test set is about about 10% of the first batch, and that's the baseline result if you train a model on 100,000 words and test it on this test set, precision recall. So this set experiment is just to see if what is the performance bound by using the second batch of a Pantry Bank added to the training data. That's the performance. If we use the same amount of cross-domain data without fully parse tree, this is going to be the performance bound. So CE2 is a real experiment. We have baseline starting with 100,000 words, and also we have baseline starting with 200,000 words. This is the performance on the same test set. By the way, this number is better than this one because this number was got at the early stage of our experiments, and in the course we changed the feature set so we get a better baseline. And we use PKU data as cross-domain data. I'm going to talk about more experiments result on using PKU data. It's not in this table. And this is similar on the English side. We trained a baseline model use about 10% of our Wall Street Journal tree bank. And the test is section 23 and 24 for those who know of the Wall Street Journal Pantry Bank. That's the baseline performance. And if you use the rest of the Wall Street Journal tree bank with a fully parse tree and put it back and added it to training data, that's the performance we got. We're going to use the LP tree bank as cross-domain data. Okay.
So what are these performance?
This is like use the Intel or training set. Okay, with 4 trees. Okay. So one question for doing this type of semi-supervised learning is that how much amount of supervision information is sufficient for us to get some gain. So this picture answers that question. The experiment was done at E1, meaning that the baseline model is trained with 10% of U-Pantry Bank, and they use the rest 90% as the EM data. So the x-axis is the amount of labels you keep. So if you keep if you don't strip all the labeling information and use the baseline model, decode it and put it back in training, in fact it hurt your model. If you keep the 18% of labels, that's the relative performance gain we can get. If we keep the 80% of a label and train a model, that's the performance gain we can get on the test set. So there's really no surprises. So the more supervision information we have, the more gain we can get.
Here you're doing this on the basis of the UPenn tree bank. Consequently, you're sure that whatever supervision you apply, it's correct supervision.
Yes.
Which is not the case
Yeah.
in the other.
Yeah, this set of experiment just is a kind of a cheating experiment to see how much supervision information we need. This is real. This is curve shows the performance if we trained with various amount of you train a baseline model with various amount of UPenn tree bank data, starting with 20,000 words, 40,000 words, 80,000 words. So the light blue curve is the F measure on the test set if you just use the UPenn tree bank. And the yellow bars are the F measure if you add 100,000 words PKU data with part of speech tagging information. And you use the baseline model to do decoding on this corpus and put it back in the training. So as you can see that we can get significant gain if the initial model was trained with insufficient amount of data. But the gain is eroded as you increase the training data. In fact, if you train the baseline is trained with 200,000 words, the performance degrades.
But that's due to the fact that the EM algorithm is wrong.
Yeah, that's right. That's right. Yes, there's a question.
I was going to say, it seems like you could also interpret it that, it seems like in the 100 case where there's a matched amount of UPenn and PKU data, there's still a slight increase. And it's only in the 200K case where there's a decrease. So maybe if you had, 200K of PKU, so there is matched. I don't know.
If I have 200, you will see that. I didn't do all that. I have slide to show the amount of cross-domain data, the impact on the performance. Yes.
If you, for example, train Collins parser, because you're using maximum entropy, right? Yes. And just get that amount of data annotated with Collins parser, and now you use it as training data. That would be a nice thing to see. If you use a different method to annotate data, what can you get from that data? Because you will have mistakes in there, the way you have it.
So you're just suggesting like co-training type of approach?
At least see if annotating with another parser that is pretty good will give you the same gain, or if it gives you more gain than you get with the PKU, then it doesn't make sense to use the PKU. If it gives you less, then this is better. Right?
Yeah, that's a possibility. We haven't explored that. Using multiple models. I'm going to talk about this is one of the future work we may do. So this is the same curve, but in relative error reduction. Yeah. This table shows that the effect of if you use the entire PKU part of speech corpus, how would that change the performance? Turns out that it doesn't make a huge difference for the small baseline. For the large baseline, I haven't got the result yet. Presumably, it won't help the performance by knowing that the fact if you only add 100,000 words, the performance degrades. Okay, so we spent most of the time working on the Chinese parser, and some student did spend a few days working on the English side. He did two sets of experiments by taking AP data. He kept all the brackets. He did this because at the time when we know the existence of this AP tree bank, we were quite excited because it's very rare to have that amount of fully labeled data. And we said to ourselves, let's just keep all the brackets and do a few EM iterations.
Who did the AP tree bank?
The summer student. The AP tree bank, I don't know. I thought you know. The Todd passed us to this corpus. But he didn't do the corpus. I don't know. We couldn't find any documentation, for example. We had to guess the meaning of those labels and tags.
Which was the one you keep telling us that you had housewives in England doing?
In Lancaster, well, this isn't Lancaster.
This isn't.
Are you sure this was even manually annotated versus automatically annotated?
This is manual. It looks like Salim knows quite well of this corpus.
Who does?
Salim.
Well, maybe it's Lebanon.
Could be. Anyhow, so one study we keep all the brackets, and later on we came aware that for certain type of constituents we have a problem of cross brackets. So clearly some of the supervision information is wrong. Then he backed off. He said, I just keep the highest brackets for highest constituent. And in all these two, in both set of experiments, it's not quite helpful to a small model. It didn't degrade a lot, but it doesn't help. It doesn't help the performance. And if you start the initial model is well trained, and then in fact it hurts performance. I think this AP track I think is precious. We haven't made fully use of this corpus, I think. And as I said, there are some style difference. Some constraints are wrong. So it's clear that we need to do more work to get it if we want to get a gain from an AP tree bank. Okay, so we're doing a semi-supervised training, and clearly there's a problem that when you use cross-domain data and you get partial supervision information cross-domain, and use a seed model to decode this data, the decoding output is going to be noisy, meaning that some of the supervision information is errorful. So we have to deal with this problem, how to train your model with noisy data. And one thing I have started doing is that thinking of methods to constrain the model. One way we can do is that, for example, parameter time. Okay, so in the maximum entropy model, for each feature we have a parameter for each feature fi. So the way we do parameter time is that we classify features into classes. And we say that all the features, for each feature you have a corresponding parameter, p sub I. And we decided for all the features in the class stage here, they're going to share one updating parameter. Okay, for those who are familiar with the iterative scaling, that's basically the formula when you updating your model parameter. Okay, so the idea here is that we want to move the parameter for feature I from p sub I to p sub I prime if only the evidence is strong enough. Okay, so this is some preliminary result. The EM data is Chinese name entity data. So if we don't do anything, just say do a plain EM learning, that's the performance, which is worse than the baseline model. And if you do a parameter time, we don't get a lot of gain, but at least it doesn't degrade the model performance. I have the result for the PKU data. Hopefully, because Chinese name entity supervision information is fast. It's only about like between 5 to 10% of words with name entity annotation. Hopefully, if we use PKU data, we have more supervision information. Okay. So the summary result is that for semi-supervised learning, at least for the corpora we have worked with so far, this method is most helpful when initial model is trained with insufficient training data. And we think it's probably most useful in the early stage of system development. Any questions? Okay, so I just started on thinking of a constraining model, and clearly I will probably do more on how to constrain model and how to classify features. And another idea would be that to make use of a cross-domain data is that they use that build a model for that corpus and use that output and use that model to induce features for the in-domain model. And the other thing we can do is that what if we use multiple models and do a sample selection as people have done in the past workshop. Another possibility is that if you have partial tree, what if you just train on the partial trees, you ignore those constituents that with missing information. Take that and see if they'll help your baseline model. Okay, so that's a conclusion my talk. Yes?
So when you train your model with the constraints from your cross-domain data, did you also do the experiments where you don't constrain your model at all? You don't constrain and use the constraints at all? And are you going to get the same best or very different best?
Well, I mean, we did this as an experiment on the Wall Street Journal UPenn tree bank, right? We strip all the label information, do a decoding, put it back. In fact, that hurts the baseline performance. Presumably, if you use cross-domain data, use data not in the same domain, that will become worse.
Well, one of the major problems is, of course, the EM algorithm, which maximizes the wrong thing. And I have this feeling that we had a speaker here, and I can't remember who it was and what he did and how he did it, but he was able to maximize, in fact, the recall and precision.
Joshua Goodman.
Really? In parsing?
Yeah, in parsing.
Well, okay. So I think that might give you a much better result, because we know from part of speech labeling and from from EM algorithm, inside-outside algorithm, that if you give it the best probabilities and then perform inside-outside algorithm unsupervised, it gets worse.
Yeah.
No, I don't think it was Joshua Goodman, because you weren't here when Joshua Goodman.
Yeah.
No, not this time. Long back.
You're talking a year ago when he came here. By the way, he came here on September 11th.
Yes.
And he couldn't go back, so he gave his seminar. Anyway. But no, I don't think
This is 96 or something. I think it's.
No, but there was also a talk. I think Andrew McCallum did something, not in parsing. He did it in some other context.
Yeah, but somebody did it. Maybe not
parsing.
parsing. But the point is that there wasn't. One did not maximize the likelihood. One maximized something that one really wants maximized. All right.
Yeah, bracketing F measure.
Huh?
The bracketing F measure. So.
Well, maybe.
I missed Fernando's talk. Fernando Ferreira, did he talk about
I don't know. It's not Fernando. You can't understand Fernando, right? Let's not kid out.
Is this a supervised learning or unsupervised learning?
No, this was unsupervised.
This was unsupervised. Maybe it was like I don't know. Okay.
With these named entities, it's even worse than 5 to 10%, right? Because even within the named entity, there is structure, and you don't even know that.
Yeah.
I mean, 5% of the words might be named entities, but you don't even know the structure inside.
Yes,
those.
we-
Most of them are at least a couple of words.
Yeah, certainly we found that the name entity corpus is not that useful. It's not as useful as, for example, PKU data.
Okay, right?
Yeah, there's a
When
question.
comparing AP news with Wall Street Journal, where the changes, they should be very inconsistent, right? Since you cannot learn something.
That's what we thought. For example, that's what we thought, but in fact, it's probably not the case. For the example I gave, that was taking that's real data. It's not that I made up. And for that particular phrase, for example, it appears in the both corpus about 600 times. So even for that phrase, you have 600 cases of cross brackets.
Right, but you can learn those, right, if they're consistent. If the same thing changes into this thing all the time, then you learn that consistently this kind of cross-bracketing will change into...
Yes, that's the one thing.
something else.
Yeah, we are thinking of, for example, we can build a model, for example, at the AP tree bank. You use that model to parse Wall Street Journal corpus. Instead of using that as training, we use that output for inducing feature. That is probably what you are thinking. Yeah.
But for something like that, how many sentences in the English Wall Street Journal tree bank did you need before you discovered that there is a discrepancy between AP and Wall Street Journal?
No, in induced feature, you don't discover the discrepancy, right? You just count in the, say, if you decide to use that feature induced from the output of the cross-domain model. You just, hopefully you will hope that the model can learn what feature will be useful.
No, what I'm saying is that maybe this is not the main issue at all, because maybe it appears once in 1,000 cases and you might as well ignore it. Because I think the more serious problem is what Fred pointed out, that for the missing parts, you don't have a good criterion, and I say you are in nobody has a good criterion.
Yeah.
Oh, wasn't it Michael Collins? I'm sorry. Because he had
Maybe it was Collins, you're
the
right.
Boulder Perceptron.
No, that was too recent, and I would remember that.
Oh, you think this was some years ago?
No, it was this spring.
Maybe it was Chris Manning then.
No, this man was practically yesterday.
Yes.
No.
I can't think.
Are you thinking of Xiaoqiang Van Noord?
Huh?
Van Noord, the Dutch guy?
I don't know, maybe. Yes,
Yes, that's
yes, absolutely. We have to look up his...
his tape.
No, we have his foils, transparencies or whatever. Yes, that's what it was.
Is it online?
Yeah, it's online.
Okay.
Xiaoqiang he was here, I think he was here last year.
This is correct. I will use you for memory. Well, I was going to make another suggestion.
Okay.
And that is that if you annotate it in the right way, part of the alternative corpus, then maybe you could use Braille learning to transform the alternative corpus to the correctly annotated data, and then use that transformation on the rest of the alternative corpus, and only then bring it in. Only then use it. I mean,
Then
they
still
can-
use it like this? Or?
Yeah, no, but you could then use it like this, but you wouldn't have to go up to the top label. You'd have it correct in various places.
In much
Because
more.
the Braille learning would tell you where it is doing things right and where it's doing.
Okay.